Okay, so I'm gonna go over this space mechanics section here. Kind of I was debating as to whether or not to do it at all, but it's going to it's going to allow me to illustrate a couple of important points, um, and also it's kind of interesting. And then there's a lot of neat little simulators and stuff online that I'm going to show you at the end that hopefully may give you a feel for sort of the topic. Okay, so what we have here when we're dealing with navigation in the solar system, we're dealing with what's called a central force problem. Well, it's when we're only considering two bodies, one of which is really heavy. We have what's called a central force um, situation. All right. So what makes a central force problem is that the force in question is a function of position, and it's a special function of position. In this case, since we're dealing with since we're dealing with like gravitation, this is given by Newton's law of gravitation, which is in vector form given by that equation. Okay, G is the gravitational constant. Big M is the mass of the heavy body, or heavy object, I guess, like the Earth or the Sun, depending on what we're talking about. M is the mass of the lighter and there's the condition here is that the heavy object is much more massive than the light object. So it's and I'll show you why that's important at the end here. And then you know, U r hat here is the radial. It's given in polar coordinates or cylindrical coordinates. Okay, and that's important. So if you have a body, so you have the heavy body, then all around it, the force is pointing directly towards the heavy body. So if you know, so if you're here, the total force is being pulled. If you have an object that's right here, it'll feel a force towards the heavy body at a but with a strength that's inversely proportional to the square of the distance. Okay, so if you're here, you may feel a stronger force, but it's always directed towards the heavy body. All right, and the heavy body's stationary. That's where this comes from. Say if they were approximately the same mass, then the heavy body would move. It would be tugged on by the light body about as much as the light body is tugged on by the heavy body, and then they both wind up moving around quite a bit. So for this formulation to be accurate, we assume that the heavy body is not moving much. All right, so just for illustration purposes, I'm going to try to write this in Cartesian coordinates. So you can look at it and tell it has a sort of a radial symmetry, right? Regardless of where you are, the force is always pointing towards the center or towards the heavy body there. So Cartesian coordinates, where we're not, if we try to write it in Cartesian coordinates, you're going to see that we're not taking advantage of that uh, symmetry. All right, so written, if we write this in Cartesian coordinates, and you can, you can verify on your own that this is indeed the truth, where r is the magnitude of the position vector. So r in this case is all right. So this, you can plug it, you can see that this is equivalent to that. Okay, I'll leave that to you. So to write we would like to write the force is equal to the mass times the acceleration, right? These are the equation of motion. And so you get Fx, well, we can just write down Fx. Fx is going to be the x component of the force, but as we'll see, it'll have both x and y coordinates involved in it. All right, so we get right, so that's just the x coordinate. And that's equal to the mass times the acceleration in the x coordinate, or in the x direction. Likewise for y. All right, so then I can expand that out. So if I plug this in here, well, first thing I can do, you can see I can cancel the mass from both sides in both cases. And you wind up with a situation where you get and that's ugly. And in fact, quite difficult to solve without just doing it numerically. So the issue is that we have a set of two coupled equations where both the x and y coordinates are present in both the x and y equations. So that makes this just observationally, you can tell that there was some sort of cylindrical or polar symmetry that would have made that a better choice. But then when you try to formulate the equations, you hit a pretty serious roadblock with this coupling between the two equations. All right, so we can get around that, even though it starts out initially uglier, if we use polar coordinates. Now, why not cylindrical coordinates. Well, it turns out that the planets orbit in what's called the orbital plane, right? And the reason is that there's all the force is directed back towards the object. So if you're up here, the force is being directed towards the object, right? So any motion that you have is you're going to start pulling, you're going to start being pulled towards the object. The idea is, though, there's nothing twisting you out of that plane. So whatever motion you have with the attraction towards the object, it's just like what we were dealing with when we were doing the tangential and normal components. There's no component that is pointing out of the plane. So you wind up always in sort of a planar motion. And so there's no need to account for the z coordinate. So in essence, we're doing cylindrical coordinates, but for brevity's sake, I'm going to ignore the z coordinate. All right, and in this case, we've already written the force, and so so the force is equal to the mass times the acceleration, and the acceleration is given by a radial component times the radial basis vector plus the the theta component times the theta basis vector. But we know what these are, so in this case we know a theta, it's got to be equal to 0 because there's no relevant force in the theta direction. Everything's in the radial direction. So a theta equals 0, but that is also equal to, if you remember from earlier on, in terms of coordinates, okay. So a theta, by definition, by definition of the coordinates, is given by this relationship. Okay. Now this can be rewritten as, and I'm going to demonstrate why here in a second, but this is the same as this. Okay, and to illustrate that point, I use the product rule here, right? So ddt of r, so derivative of the first, which would be 2r dot. So there's a derivative, so I also have to use the chain rule, right? So you take the derivative with respect to the argument, so it's r squared with respect to r, and then now take the derivative of the argument with respect to time. So that's the derivative of the first times the second plus the first times the derivative of the second. Okay, and then you can see if I divide by r, I can recover this. So if I divide by r, I get this whole thing divided by r, and that cancels with that, and I get 2r dot theta dot plus r theta double dot, which is exactly what I have here. So I rewrite a theta in this way. So this can always be done. it's just particularly, it winds up being useful here. Okay, so maybe we'll call this equation 1. And we can, because this is equal to 0, we can solve equation 1, essentially. So equation 1, I get 1 over r so I can just multiply through by r, and that goes away. And that means that this combination is a constant. If the derivative is equal to 0, if the derivative with respect to time is 0, then this value is a constant. So we just, to give it the constant of integration, h, that's what they used in the book. All right. So this is going to wind up being an important fact later on. Okay. So that's how we, that's for a theta, the acceleration in the theta direction. So similarly, all the forces in the radial direction. So this is kind of where the business end is. So for AR is equal to okay. And what we need to do, what we're hoping to do, is actually determine the path that the object's going to take, right? So if we know it's going to be something like this. Here's the heavy object. Here's the light object. And it's going to trace out a path, possibly in a circle or something like that. We just know this from intuition and our knowledge of science at this point. But so what we want is r as a function of theta, not as a function of time. Okay, so theta, marks out. So if we have r as a function of theta, then we essentially have the path that the thing, that the object's going to trace out around the heavier object. All right. So to do that, we use the chain rule, right? So okay, that should be self-explanatory. And so that's just shorthand for d theta dt. Now, just a second ago, we found a relationship between this constant h and theta dot. Okay, so we can rewrite this as where theta dot is just h over r squared. So theta dot is h divided by r squared. So I just substitute theta dot, or h for h over r squared for theta dot. Then likewise for r double dot. See, we need these in order to plug them back into this relationship. Right now this is kind of in terms of time, and we're going to eliminate time from the relationship. Okay, so now r double dot is equal to the time derivative of this quantity here, and again we're going to use the chain rule, where to differentiate with respect to time, well, yeah, this is going to equal to, this is equal to d theta, and then we multiply by d theta dt. Okay, so we use this, we kind of use this to operate on here, and we can reverse the differentiation and multiplication here. So it's okay. So differentiation with respect to time is the same as theta dot, and then differentiating with respect to theta. So then r double dot is theta dot d theta but then we already established that theta dot is the same as h over r squared. Okay. Now we're going to introduce a change of variable. The book uses like a Greek letter that I can't draw, so I'm just going to use f because it kind of looks like it. So f is equal to 1 over r, and as a consequence r is equal to 1 over f. All right. So we can plug this in where r double dot, we can plug this into this equation here, where, so this will be h. Oh, okay, so h is a constant, so it can come out. So so this is equal to h squared over r squared and we substitute in f is 1 over r, so this is h squared f squared d theta of f squared dr d theta. Now we'd like to get rid of that. We'd like to get rid of that dr d theta and put it in terms of f as well. So again, we use a chain rule. Dr d theta is the same as dr df times df d theta. and dr df, we get from this relationship. So r is equal to 1 over f, so dr df is just the derivative of this with respect to f. Okay, this is f to the negative 1, so dr df is negative f to the negative 2, just using the power rule. Okay, and so now we can substitute in for that dr d theta. So dr d theta is equal to dr df, which is negative f to the negative 2. You can see a cancellation there, times df d theta. Alright, so f to the negative 2 cancels with that, leaves the negative 1 behind, so that's negative h squared f squared, and there's nothing left except the second derivative with respect to f. Alright, now we're going to need to figure out, there's a theta dot squared somewhere. Where was that? Oh, AR. Yeah, here it is. So we still haven't figured that one out. So it's pretty straightforward, but theta dot squared, just like we've been substituting in h over r for all these theta dots all over the place. So we got theta dot is h over r squared, so that would be h squared over r to the 4th. And that equals h squared f to the 4th. Okay, so now AR, the acceleration in the radial component of acceleration here, is r double dot, which is negative h squared f squared f double prime of theta. I'm just changing the notation from this to that. So that's r double dot minus r times theta dot squared and that's equal to negative g, the mass of the large object, times r squared. Okay. Oh, so I guess we can, instead of in this, negative g m f squared. So now I have an f squared that can cancel out all over the place. So f squared goes away. This becomes a 2. This f squared goes away. Is that right? Oh, and here's this r here is 1 over f. So all these cancellations were probably a little bit confusing. So this cancels with this, and I'm just left with an f here. So I'm going to rewrite this. AR And everything's negative, so we can drop the negative signs. Okay, I can divide through by h squared. In fact, with the cancellations, this is no longer true. This is no longer the, but this is true. But, you know, I've been multiplying and dividing by f, so this is some combination of um, a relationship. So it started out as a function trying to find, you know, defined in terms of the this AR value. But with all the cancellations and whatnot, it's no longer equal to AR. It's equal to some combination of AR and these other factors. Okay, so here we have a differential equation. It's a much simpler differential equation. It kind of looks funky, but all right. And that's a pretty straightforward differential equation. And the solution is that's the solution. So you can solve this differential equation, and this is what you get as a solution. And so r of theta, c is a constant of integration. Just like h was earlier. So this is, it's like an arbitrary constant that we um, you know, it defines, as we modify c, you get a whole family of solutions, just like typical differential equations. So r of theta is equal to 1 over this. All right. I just rearranged and multiplied through top and bottom by h squared over gm, and you arrive at here. Okay, and so there's a well-known family of curves called conic sections, which are, hopefully you remember, you know, parabolas, ellipses, and hyperbolas, which have the same form. Their equation given in polar coordinates has the same form. Okay, I guess for our purposes we'll just use the plus. But all right, and it's controlled by two constants, E and P in this case. So in this, E is clearly this combination of parameters here. And then P is just 1 over that constant of integration we found earlier. Okay, so here's the solution to our differential equation. Here's the equation of a conic section. If we make this substitution, and these are all just numbers, so it's a perfectly valid thing to do, then we can arrive at, we've proven that the solution to our equation is a conic section with this definition for the parameters. Now, the nature of the conic section, you guys can look it up, but the nature of the conic section is kind of determined by this parameter E. E is called the eccentricity. And if E is equal to 0, you get a circle. Okay. If E is equal to 1, this is a parabola. And then if E is less than 1, it's an ellipse. And if E is greater than 1, it's a hyperbola. Okay. And then P defines some non-physical distance, but it's a kind of just a parameter. You can think of it as just a parameter of the curve. So look, we have two closed orbits and two open orbits, depending on this eccentricity value. So you can look at this, and if you can determine what these values are going to be, you can determine whether or not your orbit will be open or closed. Okay, if it's between 0 and 1, if the E value is between 0 and 1, you have a closed orbit, and if it's outside that range, you have an open orbit. All right, so, but we need to figure out, there's a couple of constants here, C and H, where we need to actually put real values in there, depending on our situation. Okay, so here's the heavy object, and here's the point of closest approach, essentially. And this is what we're going to call the velocity at this point. It will be called, or the speed at this point will be v0. This position is r0. That's going to be r0. And this will be at time t0, okay? So here it is. And so the trajectory will be curving in this direction somehow. We don't know exactly what's going to happen after that. But you know, it could fold all the way back onto itself. It could just continue off into outer space or whatever. But we're going to use this position to determine the values for C and H, and therefore E, I guess. Okay, so remember, H is a constant, and it's equal to this product of the radius squared times theta dot. Okay, but at this exact, and so it's always that at every point along the orbit, this is always true. It's as a constant. This product is always constant. So we can just choose this value here. So we can have R naught squared times theta dot evaluated at time t naught. I'm just putting that there as kind of a placeholder, because at this point, V naught is equal to R naught theta dot. At this point, this relationship is true. Okay, so theta dot is just V naught over R naught. So H is equal to this product here, evaluated at this point, the point of closest approach to the heavy body. All right. Now what about C? C, C is defined here. We're going to take this point of closest approach to define the situation where theta equals 0. Okay? So this will be theta equal to 0. All right? And so evaluating this equation at theta equals 0, R equals R naught, and H equal to this product here, C is given by that. And so there you go. So the position, again, just to reiterate it, where E is equal to okay, so what's important here? You know, I went over several examples of the chain rule and you know, the product rule and stuff like that. So manipulating these sort of differential equations like this is will come in handy like in later courses and whatnot. Um, it's not too terribly difficult thing to do, and it does. I've actually used it in my engineering practice sometimes, uh, so it's not a bad skill to kind of polish a little bit. And now's as good a time as any to do it. I won't be holding you guys to being able to reproduce any of this. I just wanted to go through kind of a one calculation for how this stuff comes about. And this is in the book. I just think they didn't do a terribly good job of explaining it. Maybe I filled in the gaps. Maybe I didn't. But ask questions if you need to. Um, but you know, this is kind of the upshot here. So this is the solution to the this is the path. R is a function of theta. Gives you these four options, and there's a little simulator I found online that I thought might be useful. So this is a actual to scale version of the solar system. So that's the sun there. You can barely see it, and here's planet Earth, and so we can play with changing some of the parameters around to see what happens. So here's the force of gravity, and so this is basically just integrating those differential equations as a function of time, and we can mess with some of the parameters. So in real time, like maybe we can increase. So what do you think would happen when we increase the mass of the sun? The force increases clearly because the the force is proportional to both the mass of the star in this case and the planet. And you notice that the orbit got tighter, but the energy increased as well. Well, we'll get into energy, but you notice the velocity picked up. And so there's a situation where like the further away you get, the slower you're going to be going. And so you're trading always. This is good lead into the next couple of chapters where we're trading kinetic energy, the energy of motion, for potential energy, the gravitational potential energy. So the further out you are, the higher your gravitational potential energy. Therefore, your kinetic energy, i.e. your velocity, your speed, is slower. And then the closer you are, the gravitational potential energy is slower or lower. And so you must be picking up speed to balance that, because you're in what's called a conservative force. Gravity in this case is a conservative force. There's no energy loss. So you're just exchanging kinetic for potential and back and forth. So here's the website. I'll probably post that somewhere. But feel free to get in here and mess around with it. Like you can add the moon. So like as you can tell, you can barely even see that the moon's there. But you can see the two velocities. And then if you change you can totally interrupt the Earth-Moon system by playing with some of these parameters, and the moon may separate. Yeah, like so now they've completely separated from one another. The moon is no longer orbiting the Earth. It's now just basically on a parallel, or basically an orbit about the sun. So play with it, and let me know if you have any questions.